All right, first video of the year, or I guess technically the second, but first time that we're going to look at some actual math here. So I might spend a little extra time in this video talking about some things that we can do when we're watching them to make us more successful currently and then later down the line. And the first thing I'm going to talk about is a table of contents here. So what I want you to do is, if you have your notebook out, you're going to take the first 3 pages and you're going to leave those front and back totally blank, just in case. And on the very front page, you're going to label table of contents. And what you're going to be able to do is have a table of contents so that by the end of the year, when you're studying for the AP test, you're not just spending 10-15 minutes hunting for some little nugget of information. You can say, here's what I'm trying to practice, let me go back and look at my notes, and then you can actually go through your table of contents and find it. So here's how you'll do this. So if you go to the first line on that first page of your table of contents, Unit 1.01, you could maybe go unit by unit. So you might say, okay, this is limits and continuity. So you might write, limits and continuity up here, and then you'll have all the different units down below. It might actually be a good idea. So limits and continuity. Like a little subheader, and then all the lines down below, right, are going to be 1.01, 1.02, 1.03, so on and so forth. Then what you're going to do is, on that line, you're going to write out the aim. Now, today we have 2 aims, okay? So the goal is to get this in 1 line. If you can't fit it in 1 line, there are 2 options that you have. You can condense, you're seniors in high school, you can synthesize things, but condense it in a way that you will be able to go back and figure out what the heck the lesson was on. Or, if you need to, you can take up, 2 lines. But then you need to make sure that you don't write 1.02 on that next line, you go a line down. Just make sure that you have it in a clear, concise way. Don't worry if you're going to take up too much space. Better to take up too much space than to not be able to find it later. So you write your aim or aims, and then the page on which that unit starts, or that lesson starts. So this will start obviously on page 1, but if you can just imagine, at the end of the year, maybe you're searching for, applications of the derivative, and that's, unit 3.07 or whatever, and so that's on page, 75. And so instead of hunting through, you can just go to your table of contents, look for that particular aim, and go find it, okay? So then page 1 is really going to be that 4th page, right? And so the key here is that you've got to actually label the pages 1, 2, 3, 4. If you want to use front and back, I'm totally cool with that, right? It's whatever you are comfortable with, and if you can use front and back and still your work is clean and neat, I am all for it. Obviously, if you are using the front and back of a page, so that 4th page will be page 1, and the back of that page would be page 2, and so on and so forth. And so you just want to make sure that you're numbering the pages, because ultimately that's what's going to allow you to quickly get to whatever section you want. So now, talking about that first page, for every lesson, what you want to do is just write the unit number and lesson number, right? And unit number, lesson number, and then the aims at the top there. And again, synthesize if you need to, but here you have a little more space, so don't synthesize too much. Make sure that you're able to go back and say, oh, this is what I was trying to accomplish. Did I get there? So on and so forth. Okay. So with that being said, we are ready to go ahead and get started. Okay, so to start off with, let's go ahead and take a look at this situation. So at this point, go ahead and jot down this situation and answer the question. So here we're trying to figure out what our speed is at 4 minutes into the ride. And so if you think about speed, well, speed is thought of as the distance that you're traveling within the time it takes to travel that distance. And in this situation, we notice that, look, this is a straight line, right? So the speed is just the distance over time, or the slope of the line. And since the slope of a line is constant, right, it's always the same, at 4 minutes, the speed that I'm traveling at that very instant is going to be the same as the slope anywhere else on the line, because it's not changing, right? And so I can compute the slope of this line, and that will be the speed exactly at 4 minutes. And so the speed at 4 minutes, we'll call it S of 4, is just going to be the slope of the line. And how can I compute the slope of the line? Well, let's just go from minute 2 to minute 6. And let's just pretend that at minute 2, let's say we're about 1,000 feet away from the house, and at minute 6, we'll just say we're about 2,500 feet away. And so to calculate this, I'm going to take the distance I was at 6 minutes, subtract it from the distance I was at 2, and then divide it by the time it took to do that. So pretty simply, 2,500 minus 1,000 divided by the change in the x-axis, which was 6 minus 2. And so we have 2,500 minus 1,000 divided by 6 minus 2, and that's 1,500 divided by 4, which is 375 feet per minute. Okay? And so that's the actual speed that you're traveling at this very instant, 4 minutes into your drive. Okay, that's a pretty simple situation, right? You're pedaling along, and here your speed is never changing, right? If I looked at the slope at minute 2, right, it's a straight line, this constant rate of change, so the speed is going to be the exact same. But if you've ever ridden a bike or driven a car, right, you know just by looking either at the speedometer or measuring how fast you're pedaling or how fast the road is moving underneath you, that probably doesn't happen very often. So let's take a look at a slightly different situation. All right, so here is a slightly different scenario. You're still riding your bike, right, and your distance now away from your house is given by the function d of t, and here it is graphed out. And while this is still not really very realistic, it's different in a way that will allow us to look at situations that are much more realistic. Okay? So again, your goal is to answer as best you can, what speed are you traveling 4 minutes into the ride? All right, so let's first notice something about this function. It appears that it is not linear. That's pretty obvious. And something that's not linear doesn't have that really great property of a constant rate of change. In fact, if you were to look here, right, this looks pretty flat and this looks pretty steep. So it seems like the rate of change is increasing as we go along. And if we want to find the exact speed at 4 minutes in, we can't just measure, the speed over here or the, speed right here. We have to get right there. And even more troublesome is the fact that measuring the average rate of change, like we did over here, is not going to tell us the speed everywhere else. So we might want to just abandon for a second the thought of getting a precise answer right off the bat. And let's instead think about a just very simple way of getting an approximate answer. So we want the instantaneous speed at minute 4, and we can't find it. What would be close? Well, we have a method for finding the average speed or average rate of change between 2 points. So if you wanted to find a close approximation for what's happening right at minute 4, what might you want to find the average rate between? Well, let's make it easy on ourselves, and let's say, look, if you want the exact speed at 4, maybe take the average of something that's a little more shallow and something that's a little more steep. So the average rate of change between 3 and 5. So we'll start off with an approximation, S of 4, and we'll say it's approximately. Right, let's get an approximation here. And we'll find the average rate of change between minute 5 and minute 3. Okay, so that would be d of 5 minus d of 3 divided by, right, how far did you travel? Well, you traveled 1 unit here and 1 unit here, so that's 2. Can we get better, though? So this is going to find us the slope of the line that connects D sub 3 and D sub 5. And we can go ahead and even approximate that right there. So this here is the slope of this green line. But that doesn't necessarily have to be exactly the slope at 4. So can we get even better? Can we hone in on 4? What could we do to seemingly make our approximation more accurate? Notice here that we averaged 3 and 5. Those were the 2 points we used. We went one to the right of 4 and one to the left of 4. Instead, let's try getting closer to 4. Let's only go half to the right and half to the left. And so we can move down here, right? Let's get another approximation, an even better one. And here I'm going to write this first point, so this is going to be D. It's 4 plus a half, right? So I'm honing in on 4. So what I'm going to do is I'm going to find the distance I was at 4 plus 1/2. And I'm going to subtract away the distance I was at 4 minus 1/2. And how many minutes did that take? Well, I'm at 4 minus a half here, and then 4 plus a half there, right? So it's just 2 halves or 1 minute. Okay. What can we get even closer? Right? And the answer is yes, we can get closer. How can we get closer? What do we have to change to keep getting closer? We have to keep changing the distance that we are away from 4, right? So if we keep getting approximate, keep doing the average rate of change, but we just move closer and closer to 4, we'll keep hopefully getting closer and closer to the actual speed, the actual instantaneous slope at minute 4. So imagine, let's keep going one more. Let's have another approximation for S of 4. And here we'll say it's D of 4 plus, let's just do 0.1, minus D of 4 minus 0.1 divided by, and here we've only moved, think about it, we have 3.9 and 4.1, so the total time we've traveled is 0.2, or in other words, the distance, right? We had this distance of 0.1 to the right and a distance of 0.1 to the left, so that total amount of distance is 0.2, or 2 times 0.1. All right, so let's think about our process in general. If we want to approximate the speed that we were traveling 4 minutes into the ride, we're going to focus in on that 4 minutes, and we're going to pick a point to the left and a point to the right and find the average rate of change between those 2 points. Pretty simple, right? So for our approximation of the speed at 4 minutes, we can write a general rule for doing this, right? We're going to focus in on 4, so we're going to take the distance of 4 plus some value. And let's just think about what we want to call this value, right? So this value is, in a sense, let's say, how much we're changing the x value, right? So we'll call it the change in x. And you've seen this before, the change in x. So we pick some amount that we're going to change the x value to the right, and we're going to change the x value to the left, the same amount. So then we're going to subtract away D of 4 minus whatever we pick for our change in x to be. And what are we going to divide it by? Well, the distance between these 2 points, this is 4 plus whatever the change in x was, and this is 4 minus whatever the change in x was. So we just have 2 times whatever this change in x was, or 2 times this change in x. And how can we make this approximation closer and closer to the true value? What do we need to do? Well, as we've seen here, what we need to do is make this change in x smaller and smaller and smaller. Okay, well, run that out. Take it as far as you can. Where are you going to run into a problem? Is there ever going to be a time where you're going to stop getting a closer and closer approximation? What's the smallest your change in x could ever be? And you might say, what if there was no change? What if it was 0? Well, think about that. If this was 0, if you didn't change x and you took the average rate of change based on this equation between d of 4 plus 0 minus d of 4 minus 0, that's d of 4 minus d of 4. That's the same value. That's 0. And 2 times 0 is 0. So you have an undefined function. And that's a problem, right? So what we're going to look for is, well, how close should we get, right? And with this in mind, we're now going to dive into probably the most important concept in calculus. And I'm not going to explicitly tell you how what we're about to discuss links to this, but that should be something that you are thinking about, right? If we push this to the limit, right, if we go all the way to when the change in x is 0, we run into a problem. So how can we fix that problem? What happens if I start getting closer and closer to 0? And so with this being said, we're going to move into limits. And always keep in the back of your mind, what could this connection be? How could what I'm learning help me solve this problem of finding the speed at 4 minutes? So for us to understand limits, we're going to consider this function. F of x equals x cubed minus 125 over x minus 5. And what I'd like to know is, well, what's the value at 5 when x is 5? And this function is unfortunately undefined at x equals 5. So since I can't figure out what it is exactly at x equals 5, I'd like to know, can I figure out what it is near x equals 5? And so let's think about a way of doing that. Let's imagine that we crept closer and closer and closer to an x value of 5. So I made a table here, my inputs and my outputs. And I encourage you to go ahead and try this on your own, and go ahead and plug in 4, 4.9, 4.99, and so on and so forth, and see what's happening. So what we notice is as the inputs are getting closer and closer to 5, what's happening to the outputs? What's our function getting closer and closer to? And see, 61, 73.51, 74.8501, 74.95, 985, 74.9985. Okay, but you know, we're getting closer to 5, I get that. Is that the only way that I can get close to 5? Do I have to go, 4, 4.9? Is there another way that I can approach 5? And there is, right? This way, I'm approaching it from the left, right? So 5 is somewhere over here, and I'm getting closer and closer to it, moving from the left to the right. What about moving from the right to the left? So maybe instead of starting at 4, let's start at 6, and let's get closer and closer to 5 from the right-hand side. And I encourage you to go ahead and now try plugging in these values and see what happens. Now notice, as we move closer and closer to 5, as we near an input value of 5, from the right-hand side, the output values of our function get closer and closer again to 75, 91, 76.51, 75.1501, 75.015, and 75.0015. So whether I approach from the left or from the right, even though I can't plug in 5 itself, I can get as close as I want, and I can see the closer I get, the closer I will be to a value of 75. Right, so there are 2 options for how we can write this. Most simply, one can say that f of x approaches a value of 75 as x, the input, approaches a value of 5. Okay, that's one option. However, the most common way of writing this is to say the limit, LIM, as x approaches 5 of f of x is equal to 75. Okay? And that's how we'll most commonly write it. Now, I could also write the actual expression for f of x. So you could also say the limit as x approaches 5 of x cubed minus 125 over x minus 5 is equal to 75. All right, now we're going to discuss what's called a one-sided limit. And to do this, again, we're going to look at a really helpful example. So consider the function g of x, and g of x is a piecewise function, which means it's kind of split up into different pieces. And so up to a certain point, it's defined one way, and then past that point, it's defined another way. When x is less than -4, all the way up to -4, g of x is defined by the function x plus 8. And then when x is greater than or equal to -4, g of x is defined by the function x squared minus 1. Piecewise functions can be really helpful in describing situations where, look, something behaves one way for a little bit, and then, all of a sudden it changes and behaves a different way. And so our question is, what happens to g of x? In other words, how is it behaving as x approaches -4? So go ahead and give that one a try. All right, so first let's go ahead and see what happens. How is x behaving as x is getting closer and closer to -4 from the left. So to the left of -4 is -5, and then we get closer and closer to -4, and we see, okay, g of x is 3, 3.9, 3.99, 3.999, and so on and so forth. It's getting closer and closer, it seems like, to 4. So we might say, this is getting closer and closer to 4. But what happens if we approach it from the right side? So to the right of -4 is -3, and we can then go -3.9, -3.99, 0.999, and so on and so forth. And it seems like, okay, let's look at our outputs. 8, 14.2, 14.9, 14.99, 14.999. And it appears here that as I'm moving from the right-hand side and getting closer to -4, approaching -4, that the function is, the value of g of x is approaching 15. Okay. So from one side, it's approaching 4, and from the other side, it's approaching 15. And hence, we get one-sided limits. All right, so how can we write this? Notice that what we've done is we've found two limits, but they're different in that when we approach it from one side, we get a value of 4, and when we approach it from the other side, we get a value of 15. So let's start with approaching from the left-hand side. So we write the limit as x approaches -4 from the left-hand side of g of x is equal to 4. And if we wanted to approach from the right-hand side, we could talk about that limit as x approaches -4 from the right of g of x is equal to 15. And here's what determines which limit, which side I'm talking about. So if I want to take the limit approaching from the left-hand side, the more left I go, that's the more negative side, right? So if I'm thinking about I want to approach -4, approaching it from the left means I'm approaching it from the more negative numbers. And so I'll use this superscript, like if it was in the exponent, right, of a negative. And that tells me that I am approaching from the left. And if I'm approaching from the right, well, to the right of -4 are more positive numbers. And so I use the positive superscript there to denote that I'm approaching from the right-hand side. And so this leads us to something pretty interesting. What do you notice about these two limits? Well, you should notice, look, they're not equal. So when I approach -4 from the left, and when I approach it from the right, I am not getting closer and closer to the same number. And since they are not equal, this means that the limit as x approaches -4, the two-sided limit of g of x, well, this does not exist. And sometimes you can denote that as DNE. The limit as x approaches -4 from both sides does not exist. Why? Because it's approaching different values depending on the side you're on. And so this leads us to how to define a two-sided limit. All right, so this leads us to the definition of the two-sided limit. So the two-sided limit, written as the limit as x approaches a, notice it's the two-sided limit, there's no superscript here, of f of x is equal to L if and only if the limit as x approaches a from the left and the limit as x approaches a from the right of f of x are both equal to L. And this means what you might have expected, right? If you want to know whether the two-sided limit exists, then you need to first check the left one-sided limit and the right one-sided limit to see if they are both the same. And if they are, then that's the two-sided limit. If they're not equal, well then just think about it. The function is approaching different values from either side, so the two-sided limit doesn't exist. So let's go ahead and now apply this definition and our method by getting closer and closer to the value that we want to approach in order to actually compute some limits. So I'm going to give you 3 questions here, copy them down and show your work, and we will discuss them in class. Here I'm referring to the question at the beginning of the video about the speed of the bike rider at minute 4. And so think about how our new concept of limits might help us find a very precise answer to that question.